Okay, so let's do another example. It says verify Stokes' theorem when S, the surface, is the set of x, y, z with the condition that x squared plus y squared plus z squared equals 4 and z is greater than or equal to 0. And our f function here is I plus xj plus yzk. So let's first graph this surface here. So x squared plus y squared plus z squared equals 2 squared would be a sphere. But we have the condition that z has to be greater than 0, so it's going to be half a sphere. So let me graph it. And the radius of the sphere will be 2. So let's graph the sphere, semi-sphere. So it would look like something like this. So it's half the surface of a sphere, so the upper half of the sphere with radius 2, centered at 0, 0, 0. So we need to parameterize this. So let's recall spherical coordinates. Okay, so here's recall our spherical coordinates system. So z equals rho cosine phi, y equals rho sine phi sine theta, x is rho sine phi cosine theta. And the phi angle here is measured from the z-axis, so let's see here. So if I call this guy here the z-axis, and this is my rho vector here, the phi angle is in here. Now we want to just have the top portion of the sphere. That means that phi angle usually can go from 0 to pi all the way down here. But in order to pick up just the first half, the top of the sphere, the phi angle will go from 0 to pi over 2. So therefore we're going to have to change this guy to pi over 2. So let's do that. So I've changed it to pi over 2. And also in our case here, looking at our surface up here, the radius is 2. That means our rho value would be 2 here, here, and here. So let me change those. Okay, so I've made those changes. So now we can write our parameterization of the sphere. Let's call it R. Okay, so our parameterization of the upper half of the sphere would be given by 2 sine phi cosine theta for the x component, 2 sine phi sine theta y, 2 cosine phi z, where theta goes between 0 and 2 pi, but the phi angle is now going to be restricted between 0 and pi over 2, because again we're going to pick up just the top half, so the 0 to pi over 2. Okay, so let me draw the D region now. So this is what our mapping would look like. Using theta and phi. Usually we use u and v, but it doesn't matter. In this case, I'm going to use theta and phi is more natural. So the theta goes between 0 and 2 pi, the phi goes between 0 and pi over 2. Then under this mapping R here, we'll map into the top half of the sphere, a radius 2. Okay, so let's keep going now. Let's start to verify Stokes' theorem now. Okay, so R up here is my parameterization of the upper half of the sphere, of radius 2. I have my f function over here, and here is a statement of Stokes' theorem. It says the line integral over f here equals the flux of the curl of f across S. So C here is the boundary. The boundary would be this circle at the bottom here. We'll come back to that in a second. So to verify, we have to show the two sides equal. So let's first focus on this side for now. Okay, so let's work on that side. Okay, so we're doing the double integral side. So you know by 15.6 that the flux can be computed this way. So we're going to have to find now derivative of r respect to theta and respect to phi. So let's do that. So doing r respect to theta first. Looking up here, derivative of cosine theta would be minus sine. So that's why I got minus 2 sine phi sine theta. Moving on to this one then, this guy here would be derivative of this guy respect to theta would be cosine. So I got that. And this one doesn't have any theta in it. We're treating phi as a constant, so therefore it just gets 0 in this component. Let's do r of phi next. So r of phi then, well, looking at the first one, derivative of sine of phi with respect to phi would be cosine, so it would be 2 cosine theta, and this will be also cosine. And last one, derivative respect to theta, be minus sine. That's how I got that one. Okay, so now let's do the cross product of these two guys. Okay, so here's my cross product. I have my r theta on top, r phi on the bottom. So let's do the I component first, so let's cover this. So it'll be this times that, this times that. So let me write it down here. So I get this, so again I went 2 times negative 2 would be negative 4, then sine phi times sine phi squared, and times cosine here, and then 0 that way. Okay, let's do the j guy next. So it'll be this times that, minus this times that. There'll be a minus sign in front also. Okay, let's do that. So we get this then, so I went negative 2 sine phi sine theta times this guy, become 4 sine phi squared sine theta, and then 0 times that, which is 0. So lastly, let's do the k one. So we get this, so I went negative 2 times this will be negative 4, then be sine phi cosine phi sine theta squared, and this minus this way, so it'll be negative 4 here, sine phi cosine squared, cosine theta squared. So notice they both have the negative 4 cosine phi here and here. Let me factor that out from the k component here and simplify it a bit. So I factored out the minus 4 sine phi cosine phi here, then I have a sine squared plus cosine squared. This actually should be a plus here, not an equal here. And then that's just 1 there. So this just collapses to the negative 4 sine phi cosine phi k direction. Okay, so we get this there for the k component. Okay, so let me just erase some things and summarize what we have then. Actually, before erasing this completely, I just want you to notice that the I term, the j term, and the k term all have a negative 4 sine theta. So I can factor that in front. I'm going to do that when I summarize it at the top. So I'm going to factor out the negative 4 sine phi out each of these terms. Okay, let's get going. So summarizing this, what we have our r theta cross r phi here. So now we're going to have to compute the curl, so let's do the curl next. So here's my definition of curl. Again, my f's over here, it's 1 in front of the I, x in front of the j, yz in front of the k. So you got 1, x, y, z, and then you have your del operator up here. So partial respect to x, y, and z. Okay, so let's start doing this. So let's do the I component first. So it'll be this acting on that, this acting on that. So right over here. So we get this. So again, we have our partial y operator acting on yz here. Then subtract partial z operator acting on x, which you have here. Okay, let's do the, we'll come back and compute this in a second. Let's do the j component next. So it'll be this operating on this minus this operating on this with a minus sign in front. So let's do that. So doing that, again, we have our partial x acting on yz, which I have here. Then minus partial z acting on 1, which I have here. Okay, so lastly, do the k component. Okay, let me do that. So we get then our partial x acting on x here, partial y acting on 1, minus, sorry, it should be a plus here. Okay, so let's work these out. So the top one, partial y operator acting on yz, so treating the z as a constant, so derivative y is 1 should just be z there. So it'll be z, not 0, so it's going to be zi, and partial x operator acting on yz, that'd be 0, and partial z operator acting on 1 at 0, so it'd be 0j. And partial x operator acting on x would just be 1, and that'd be 0, so it just looks like it'd be k here. So this is our curl. Okay, so now I think we're ready to start doing the double integral. So let's summarize. Okay, so here's our double integral. So we know it's going to equal this. We got everything we need now to start plugging into this. So let's look at some of my curls here. So looking up at my R parameterization of the S surface, this would be X, Y, and Z. So I've labeled up here X, Y, and Z. So it's going to be curl composed with R theta phi, sorry. So it'll be Zi, but Z now is 2 cosine phi, so it'll be equal in here. I'm going to go theta first, and then phi, so phi is going to be on the outside, so it'll be 0 to pi over 2, because phi goes from 0 to pi over 2 here. And theta will go from 0 to 2 pi. Then it's going to be Z, but Z now is 2 cosine phi I 0j plus k, and this guy dotted with R theta cross R phi, which is right here, so let me write it right here beside it. So I get this then. So we're going to have to dot this, so we're going to go the I component, so the sine phi cosine theta, this negative 4 sine phi will come along too, times this one. There'll be no j component because there's 0 here. Then it'll be cosine phi times 1 here. So let me write that out. So I get this, so it'll be negative 4 times negative 2 will be negative 8 there. That'll be sine phi squared, cosine phi, and the cosine theta. That'd be the I one, be no j. And the k one would be negative 4 sine phi cosine phi right here. Okay, I can pull out a negative 4 outside the integral, say, let's do that. So I get this then, I factor out the minus 4 in front here. So then we have to integrate this first guy, so with respect to theta, so the phis are constants, so the integral of cosine theta would be sine theta here. And again, these are both constants with respect to theta. So integrating this, just be a theta in front here. So let's do that. So integrating, I get this again. So again, the integral of cosine theta would be sine theta. And integral of this is just a constant. Just put a theta in front of it. So now I'm going to put the 2 pi in place of theta and then put 0 in place of theta. But notice here, if I put 2 pi there and 0 in there, the sine of 2 pi is, so sine of 2 pi is 0, and the sine of 0 is also 0. So therefore, that would actually disappear, this part. And I just left with this one, so let me write it out. So I get this, I just noticed I forgot to put a d here. Okay, so we'll get this then. I'm going to use a let's say W substitution on this guy. So I'm going to say let W equal sine theta. Sorry, I meant phi. So W equals sine phi. So then dW d phi will be then, so dW d phi will be cosine phi. So dW will be cosine phi d phi, which I can substitute right here. Okay, so let's rewrite this guy over here now. So I get this right here. I pull out the 2 pi with the negative 4 to give me negative 8 pi here. Then making the W substitution will be W dW. It's going to be W of pi over 2. But my W is sine. So sine of pi over 2 is 1. So it's going to be 1 up here. And the sine of 0 is 0. So it'll be 0 down here. So then integrating this, we'll get W squared over 2. So let's do that. So I'll get negative 8 pi times W squared over 2, evaluate at 1 and 0. So when you put 1 in there, just you put 0 and it's gone. It's just going to be, I'll let you check, it's going to end up being negative 4 pi. Okay, so that's the double integral side of Stokes' theorem. So we still need to do the line integral side and show it the same as this. But I'm going to do that in another video, so I'm going to leave it there. So we'll do part 2, where we'll verify the line integral should be this number also. Okay, so let's leave it there.